So last week we talked about this question, which is about counting the appearances of these two numbers from 00 to 11. So we have 8 numbers in total, each in 2 digits, like you can see here, two-bit binary numbers. We have 8 of this, and we are so these 8 numbers could be 00, 01, 01, 01, 11, 10, or something. So we need to count how many times does these 4 numbers appear. So we talked about some intuition in terms of how to solve this. So you can see over here, we have a 2-fold decoder. So the job of the decoder is the following. So our input will be one number. Let's say the first number x0. So we have x01, x00, and so 2 bits. And we put in a 2-fold decoder, what's going to give us? It's going to give us a 1-hot encoding. So which means if A0 is 1, means 00 appeared. Or if C0 is 1, that means we got 1, I think it's 1, 0, right? So which means the input is 10. So which means we are transferring a binary input into a 1-hot input. Why is this going to benefit us? Think about the following. For the 8 input numbers, we use 8 such decoders. So what we will have from A0 to D0 and A1 to B1 until A7 to D7. Then what's come naturally is the following. If I want to know how many times does each number appears, I just need to count how many A's are there, how many B's are there, how many C's are there, and how many D's are there, if you agree with me, right? Okay, so in this step, I hope everyone is good with the decoder stuff. This is the first step to solve this question. Then the next one would be, okay, I didn't have anything here. So let's get started with a new page. We will have, remember from the previous stage, we got A0. Let's just count the appearances of 00 first. So let's start from A0, A1, A2, A3, A4, A5, A6, and A7. So each of these are just 1-bit numbers, right? So what we need to do is actually the following. So number of 00 equals to summation A0 to A7. This means a 1-bit summation, which is like 1 plus 1 plus 0 plus 1 plus 1 plus 0, right? That's the thing we are trying to get. So can anyone have an intuition what kind of blocks we're looking for here? We're doing these, a lot of adders, right? A lot of full adders. So of course, you will need to think about how to efficiently use these adders. Of course, you can use, let's say, first let me ask a question. How many bits can there be maximally if we have like 8 inputs? What's the maximum number you can get from 8 inputs? The summation. 8 inputs? Are you sure? 8 1-bit input. So which means 1 plus 1 plus 1 plus 1. What's the maximum number you're going to get? It's going to be 8, right? How many bits do we need to represent it? 4 bits finally. So the first intuition, you can change 80 into 0001. Like A1 into 000, which means append 3 zeros in front of it. And then we can use such the 7 4-bit adders to directly solve the problem, if you agree with me, right? So for example, A0 is 0001. Then A1 can be 0000 and got a plus over here. So the final results, this is the sum. Now we move to A2, which is maybe 0001. And I got 0010. And I can continue all of this until I reach the end. But you can see something is not quite good here, which is it's so less efficient. We have got so many 0 plus zeros here, right? So another solution would be trying to build step by step, which is do how to say it. Remember how we can constitute, let's say we talked about the, how to say, remember the carry local head adder. So we'll first construct a adder of 4 bits using 1-bit adders. Then we use this as blocks to constitute a 16-bit adder. So which means everything can grow exponentially. Similarly, what I can do, of course, we start from 1-bit addition, right? And doing 1-bit addition in our case is following, which is, let's say we have adder. I put an adder symbol here, which we have input A and B. We have, this is, let's say, C in over here for the carrying. And we got C out over here for carry out. And the other branch we have is the local summation S. Okay, so let's try to use this symbol for over here. Firstly, A0 plus A1, we can just do 1-bit summation. Similarly, A2, A3, and A4, A5. That makes sense, right? Just try to add them up, connect to AB. So can someone tell me, what number should I put over C? Just to ground it, right? But, yeah. But what if there are more inputs? We can leverage the scene to add 3 numbers at a time, right? So be flexible about this. But in this case, because we have how to say 8 numbers, so you can see 8 can combine into 2, 2 combine into 1. So which means using this might be better. So what I'm going to choose to do is to ground all of these. Of course, if you're drawing in future exams, make sure at these intersections you need a dot to indicate there's an intersection. Otherwise, because in digital circuits we have so many intersections, if there's no dot, we assume there's no intersection. Okay. Okay, so we finished the 1 step, which is we now combine 8 1-digit number into 4 2-digit numbers. Why is 2-digit? Well, we have C out, right? So which means I can do some annotation. Speak of this is pretty awkward. I got myself confused the last Friday, and I stuck for like 5 minutes in front of the Friday class. That's really awkward. But you can see what I'm trying to do. So now let's do some notation. Here is as let's say 0, 1 as 0, 0. Remember, C out is the highest because it's carry out, right? So it's going to be 1 bit higher than the S, than the local sum. Similarly, we have S11, S10, S21, S20, S31, S30. Okay. So the next step, now we need to do some combination to combine the 2-digit numbers into 3-digit numbers, right? So if you agree with me, we cannot produce 4 digits using addition of 2 digits, if that's right. Even 11 plus 11, what we are going to get 110. So we can't get anything higher than that. Okay, so coming back, what I can do, remember how can we build a 2-digit adder? We just the easiest way, of course, you can do carry local head adders, do this fancy stuff, but the simplest way would be concatenate 2 full adders to make a 2-digit adder, right? So which means I can, let me paste 2 adders over here. It's okay, I remove the top. So what am I doing? Just a summation of all of these. And so what I'm going to put here is the following. I'm putting 2 cascaded adders. So that constitute a 2-bit adder. And the output will be 3 bits. So I'm connecting the C out into the C in over here. Then how to use this adder? That's where I got confused last time. So remember, each adder is going to process 1 bit. For example, like what we're adding 1, 1 to plus 1, 1, just like the example just given. You first combine these 2, and I got 1, 0, so the carry out is going to be 0. Then I combine these 3, C in A and B to got a 1, 1, right? Similarly, we are following the, so the higher base goes here, which S01 and S11 goes here. And the lower base is going to be taken care by the lower adder. And C, of course, is still grounded. But you can see in some cases, let's say we have some more numbers, we can accommodate 1 more input over here. one bit input over here. But here we don't have that, so just ground it. And so for the S, let's give it a name. So for this one, S42, S41, S40. Okay. And we can just do the same for the lower branch, which is do something like this. And let me change the annotation. So again, don't forget we combine the upper or the higher digit for adder is going to take up bit number 1, and the lower part is to take care of bit number 0. So which means you got S21, S31, S20, S30, and grounded. So S52, S51, S50. And everyone can see what I'm going to do next, right? Just to go one more step, which is, let me still copy my lovely errors. But this time, one more. Okay. So now it's 3 bits, and we are doing 2 internal connection over here. And so for the output, what we're going to have is 4 bits, which is S62, S63, S62, S61, S60. And for connection, again, still one adder take care of 1 bit. That is, the highest bit goes to the first one, the middle bit goes to the middle one, and the lower bit goes to a lower one. Then we'll do it. So finally, this is the number you're going to get. And if you agree with me, that's a summation of the 8 numbers on the left-hand side. So we are using 3 steps of these 2 components. You see, 4 1-bit adders, then 2 2-bit adders, finally 1 3-bit adder. Then we'll do it. I hope this question is clear. And if we move back, again, you can repeat the circuit for B0 to B7, C0 to C7, D0 to D7 to count all the 4 numbers. Then there's the follow-up over here and trying to modify the output to find the most often number. Let's see, let's create a new page. So this is, I think, pretty much related to the first question, which is which I refer to this one. We are trying to get the, wait, I think we directly solved it, isn't it? So I think this will provide a solution. We have 4 inputs, and we want to output the, wait, this time not index, right? We just need the maximum number.
Well, it's the maximum number. It's not the maximum. It's just the one that appears the most often.
Oh, so still the index, right? Okay, then we can just use it. But this time, remember in this question, we're talking about if there are, let's say, 2 numbers with the same value, 43 versus 43, we will take the lower index, right? So which means, for example, if this one is similar, is the same as this number, what we will do is we will output 0, 0 as index. But this time we will try to output this one. So remember we had a please.
I think this is about not the lower index, but the higher number, the higher value, right? Because it says the higher number wins.
Modify circuit also the 2-bit number that appears the most often.
Higher number wins ties.
So higher number wins ties. In this case, in a previous example, the lower number wins ties.
Okay.
So what we can do, I think we discussed this before. Remember, the reason we are assigned the basis S0001, 1011, the 4 number, is only because if we have a tie, then we have a greater than A gets, only if A is greater than B, we'll take the upper branch. So how about we do the reverse, which is we put 0, 0 over here, put 0, 1 over here, and 1, 0, 1, 1. So which means so x00 to x11, x01, x10. And over here, What does this mean? So x00 means the number, the time, how many times does x00 appears? Similarly, x11 means how many times does S11 appears in the 8 numbers. And let's say we don't have x00 or 01. 10 appears 4 times and 11 appears 4 times. So we have 0044 over here, right? And what we need to do is compare 4 and 4. Is 4 greater than 4? Not right, not really, right? So we'll be selecting this branch B all the time. Then winner will be this one. And after this circuit, remember these circuits are just meant to output the index of the corresponding branch is being selected. So which means finally F1, F0 will be correspond to these, which is X11. But if you're unclear about this circuit, just refer to the last time. I can give you a short recap, which is you have a magnitude comparator over here. So this small module have to be take care of. You can see the multiplexer takes just the raw input A and B, and we have magnitude comparator. If A is greater than B, then output will be 1, right? So we are selecting A. Otherwise, we are selecting B. So this circuit, what it does is just output the maximum number of A and B. Similarly, this one is output the max number of these two. Again, because the order I'm numbering it, if we have a tie, then the lower branch always wins. That's why we put the higher index or down below. Okay, and follow up, we just analyzed what are the relationship in terms of, so F1 is going to be a function of these, of course, this magnitude comparator. So we have a winner for a semifinal. We have another winner for a semifinal. So we want to have a final winner for the final, right? So, so over here, we need to find the relationship. We have 3, GT1, GT2, GT3. So which means the numerical relationship of these 4 numbers, right? So now we need to find what is the relationship with of X1 with respect to GT1, GT2, GT3, and what about F0? And you can, of course, we can list the truth table or whatever you feel like, for example, program like style, and you will find out the following, which is F1 is just equal to GT3, which we can just put it here. And for F0, which is the lower bit of the index, you can see, by the way, the F1 means the higher index, which is the X10, X11, the 1 over here. So the lower branch, if lower branch wins, then F1 will be 1. If outer branch wins, F1 will be 0. And F0 take care of what's inside. So if the upper branch of each of these units wins, then we have output 0. If the lower branch wins, then we got 1. So which means you can think about the. So firstly, we got a multiplexer. Then the GT3 is a selection signal. It's going to tell us our final results. Does it come from here or come from here, right? And these 2 inputs just provide information. If, let's say, I select the lower branch, then which of this number is larger? So I output the index, either it's 0 or 1. So I put F0 here. But this is a very rough recap. If you are, if you're puzzled, make sure you check out what we had last week. Yeah, we have recordings posted online for this question. Is everyone good with this? If so, I will move forward. Any questions?
Yeah, I have one question.
Please go ahead.
One we built, scroll down. If you go back, scroll down. Yeah, like I guess it's
this one.
Like, okay, this is adding up all 8 of the 2-bit numbers, right?
Mm-hmm.
Doesn't it ask us to tell, like, because we give it 8 2-bit binary numbers, and it asks us to tell it how many times each, like each. So in our addition, each time like 0, 1 appears.
Yes.
How is this doing that?
We have to do this.
We have to do this first.
Oh yeah, okay.
To give the zeros and ones.
Yeah.
And how many?
Okay.
So how many ones are in the A? How many B's are in the B? How many ones are in the C? Then we connect it with this C. So that's why I'm putting A0 to A7 here. But nice question. Go ahead.
Would that be considered an optimal solution for this? Like, would we be okay with this on quiz, like this type of answer?
That's a good question. I would say I can't think of anything, even better. Let's say, for example, we make more sufficient use of the first layer inputs, which means I can put maybe A6 and A7 to some. Let's say, can we just use 2 adders in the first stage? Then we have 4 free numbers, right? I can hold 1, 2, 3 additional bits over here. I hope you agree with me over here because these things they can take in another extra number as input, right? So which means I can move A5, A6, A7 probably over here, but still one more. So which means I have to use at least the 3 adders over here. Then you will have let's say S0 still 3 two digits numbers. And we have additional A6 and A7, but okay, but then we still have a problem, which is, let's say the upper 2 branches won't change, except for we might put A6 over here. If I put A6 over here, then my output will still be 3 digits. But over here, even I put A7 combined with these 2 numbers. Wait. Now we only have S21, S20. So the next step will be you will have to try to combine 3 digits number with a 2 digits number, which I think still requires a 3-bit adder. So we still need a 3-bit adder over here. So the answer might be yes. So you might need to can save a couple of, but that's a very nice question. I mean, you might able to save a couple of these. Let's directly give it a try. I want to make it more clear since you proposed it. First, let's copy the structure and we'll try to modify it. I found that could be easier way to do. So like I said, you could just remove this adder, right? Then we don't have this number over here. Okay, so this is what we are going to get after the first stage. So for next stage, of course, I can combine these numbers and I can put A6 over here. That's what I'm suggesting. So similarly, I can put not really. It's not. I don't think it's necessary to use it over here. So we can remove these, right? And I can put A7 over here. And I can put what? 505152. Okay, how about these? This is what I can do. So we have a 2-digit number here. Let's pretend it's 3 bits. So I can put it over here. Please go ahead.
Perhaps could you use the carry in for the first level?
Carry in for the.
Where you did A4 and A5, can you do A7 there?
You've got 3 adders on the far left. If you do, like for example, for the top ones, you do A0, A1, A2, and then for A, B, and C.
A0, A1, A2. I see. You want to put A5 over here.
Yeah, I'm saying for each of the ones in the first level, you have A, B, and C in each corresponding to 3 of the A1, A2, and 3 corresponding to.
Okay, can you do it in 3?
Okay, I see. That would be possible. But let's compare this though. Let's try to finish what we have right now. But you see, the key idea is try to leverage the scene as much as possible, so we don't waste errors. Now we are still ground a few things, so it's some kind of waste. But if I finish this, I can just put a 0 here, right? That will do it. So how many errors did we use over here? That's 8. But let's try what you are saying. That's a good question. So what if we try something at the first stage? So now we are simplifying these once more. So let's give it a try together. Honestly, I don't have a immediate answer in mind, but I can definitely try it. So what you are suggesting is let's even don't use this. I can put okay. I will try to put A4 over here and A5 over. Is that what I was suggesting? Great. Then okay, so we still have two digits number here. So which means these two adders are still necessary because we need to combine these two digits numbers into a 3 digits number, right? And I already put A6 over here. So which means in worst case, this can go to 111. And okay, then we don't have this in intermediate. So now this is what we have. And we need to add additional A7 to it. So which means we are doing a 3-bit plus 1 bit. I think it still takes a 3-bit adder, right? We need to be able to handle 3 bits, right? Which means I can do A7 over here. Okay. So S42, S41, S40, these are 3 bits, and I put 0, 0, and maybe ground this. So how many? Okay, in this case, we are only wasting 1 terminal for C. Great. I think that's a more, how to say, compact solution. Thanks, that's a nice catch. So I think by doing this, you kind of emphasize understanding of this one. Nice, thank you. Okay, so let's move forward. As I have been talking about, we're roughly 1 hour behind the Friday lectures. I'm trying to chase them. So, every time I have to do some preview over here. So let's close this down. But this is, I think we talked about this for 2 lectures already, about one's sign magnitude, one's complement, two's complement. Here is a requirement, everyone. Make sure you are very comfortable with, all of this conversion, which means a positive number to negative number to one's complement, two's complement. And if you give any of these 6 numbers, you can write the whole table for any number. Even, for example, sometimes what you're giving is -23. Ask you to write down all the rest. You should be do it very quickly and accurately. So what I would normally do is the following. So let's try to look at example. So this is asking you to express -17 as the 8-bit sign magnitude, 1's complement and 2's complement. That's the example. So firstly, can someone tell me what is 16? 17. 17 is 16 plus 1, right? So which means we have 16, 8, 4, 2, 1. That's number 4. So anyone verify that? Should be 0, 1, 2, 3, 4. 2 to the 4 plus 2 to the 0. That's 16. That's okay, but we need an 8-bit sign. So if I'm trying to represent plus 16, what's going to happen? We just put a bunch of zeros over here in front of it, right? A side question, what is going to be 1's and 2's complement of this number, not plus 16? Just to copy it. Make sense? Okay, so what about -16? Let's start from sign magnitude. So just to swap the first bit. So remember, this is for numbers. This is for the symbol. So we just copy 0, 0, 1, 0, 0, 0, 1. That will do it. Simple and easy, right? And the next step, By the way, as you saw in the class, there are at least 3 ways to do this conversion. But I'm picking the easiest one, which is, let's try figure.
Two's complement.
Oh, for one's complement, sorry. But we will do all of these. So for one's complement, just let's say minus 17. So we just copy this one. And compare to the sign magnitude, okay. Copy the symbol because you make the complement won't change the symbol. It's a minus number, it's always going to be a minus smaller than 0. Then I just flip all the bits over here. So you can see 1 to 0s, 0 to 1s, flip it. But another thing is I'm trying to have you understand why we are doing this. In case function, what if it's not a binary? Would it be still flipping or some different behavior? So by definition, what is one's complement? It's going to be 2 to the n minus 1, right? Minus x. That is going to, and this is once. And 2's complement by definition is 2 to the n minus x. So for this one, let's say for 8 bits, what is 2 to the 8? 2 to the 8 is 256. And if you are representing binary, it's going to be 1 trailing by 8 zeros. So if I do a minus 1, I do a minus 1 here, the borrow here. So we can decompose these into 1, 1, 1, 1, 1, 1, 1, 8 ones plus 0, 0, 0, 0, 0, 0, 0, 1, right? So you can see this is so this is 2 to the n, and if this is going to be 2 to the n minus 1. So if you use 1, 1, 1, 1, 1 to minus 1, 0, 1, 0, 1, 0, let's say, now of course what you're going to get is to flip the bits, right? So that's kind of course, but in this conversion, if you're doing from this direction, here x means the positive number, which means you are using okay. But how about let me finish the first one before I go to the so I don't confuse you. Let's keep these dots for the next page. Speed up. But you kind of see this is definition, right? But for this, for binary, it's more practical to just keep the, I mean, if we start from sign magnitude, sorry. And we want to go to ones, you can just keep the symbol bit and flip the number. And for the 2's complement, we just do add 1. Right? That will do it. But if you look at this example, we're trying to get minus 17. So x equals to 17. This is very important. Because for a positive number, it's just the x, and one's complement is x, 2's complement is also x. Only if x is smaller than 0, we will have to use this how to say 2 to the n minus x or 2 to the n minus 1 minus x. So which means we are going to have so for one's complement, we are going to have 1, 1, 1, 1, 1, 1, 1, 1 minus the number for 16, which is this one. This is plus 16 or x, and this is 2 to the n minus 1. So we are getting is 0, 1, 1, 1, 1, 1, 1, 0. And finally, for 2's complement, just add 1. 1, 1, 1, 0, 1, 1, 1, 1. Is that a bit same? Okay. So you see 2 aspects of these. This is more, how to say, from the definition. We know we are representing a number which is going to be minus something. Then we find x equals to 16. Then we can go to the definition by one's complement is 2 to the n minus 1 minus x, which is 8 ones. If this is, of course, if 16 bits, then n equals to 16, we have 16 ones. And we subtract it with these, with x. Then we got one's complement, and 2's complement is just a plus 1. Okay, so that will do it. So that's for what's remaining last week. And let's take a 5-minute break so we can start a new slice. It's not the end of the quarter, don't worry. Sorry. Oh, by the way, if you if any of one of you going to attend the evening session, remind me to how to say something about this one, because I want to I think the other discussion session students didn't hear it. They just how to say take the original solution as granted. That's how to say more intuitive, right? Because we have 8, 4 to 1 such a periodic structure. But if you want to squeeze it to the full 610, this might going to work.
I think we explained it, but why can't we connect 42 and like 42 and 40?
I think they just represent the
Wait,
different digits. of a
I started to
single
think
number.
about
Because like why do we have to have those two grounded?
these two.
No.
This one, this one.
Yeah. Like why can't we just combine it so we only have two?
Let's see.
4, 1, and 14 have different significance. 14 is worth twice as much as 4.
Yeah.
Okay.
So that's a three-digit number. Let's say 111. Worst the case. So if we are going to do a +1,
Oh,
then we
you're
are going to
saying
go
place.
actually 1000. That's the worst case you can think about, which means I need 3 errors. Well, you can see I'm wasting 3 branches over here. That's right. But I don't think we can do anything on it because that's it. S41. This already means 2 to the 1, right? It means S41 times 2 to the 1. That's the significance of it. But A7 means A7 times 2 to the 0. So it can only be combined with something S40 times 2 to the 0. But that's a good catch.
Okay. That makes sense.
I might be able to make mistakes because I never think about this carefully. But it seems like to be the best thing I can think of. Right. So this is the best, most compressed way I can think of. Great. Okay, here comes the second half, and because there are so many calculations down here, I will try to pull up a local copy of my answer that I produced last night to compare it. Let's see. Okay. I think actually it's pretty safe to skip this, right? Because this for Friday class, which try to remind him after a week. If ask you to just add 2 unsigned numbers. So if these 2 are just unsigned numbers, I'm just do some clarification because I remember someone asked it last night. I mean, how to just add on. If I just add it, just to do it bitwise, just like you're doing that for base 10, but this time just if you see if see 2, then make it 1 0. So I got 0. Here I got 1 plus 1. Sorry, I made a mistake. And what is 1 plus 1 is 2. So I got 1 0 and 0 0 1 going to give me 1. Similarly, 1 0 here. 1 plus 1 is 1 0 here, and finally 1 small mistake here. So 3 1s, that's 1 1. Finally 1 0. So that will do it. Similarly for subtraction, if it's unsigned, then it's very easy. Just 1 0 0 1 minus 0 1 0 0. So if you are borrowing something, for example, you are borrow a 1 over here, so you can make it a temporary 2 and deduct it to 0. Does it make sense? So for this part is still 0 1. So over here I need to borrow something. So I can borrow. Borrow means I can temporarily understand it as 0 2. So what I get is 0 1 0 1. But for this kind of thing, sometimes it's pretty clear that 1 0, which is 2 minus 0 1 is going to give me 0 1. but you just do it bitwise, one by one. It's nothing different from what you do for base 10. Just don't do anything, don't have any number beyond 2 over there. Okay, so question, moving forward, actually you just saw this, but that's why I'm saying you need to practice this kind of things, trying to move it back and forth. So this is sign magnitude. And what is the decimal number is representing? Firstly, it's a negative number. And the value is going to be 10111, which is 16 plus 7. That's 23, right? So I got minus 23. Of course, if you're not so familiar with these, you can just do it slowly. But 10111 asking for what binary number is, that's going to be trivial for you guys. And just look at the first one. So for the wait, why is this sign? Oh, okay. This time it's just a plus 23. Because the sign is 0, which means we got a plus sign over here. So for 1's complement, unfortunately, it's going to be a negative number. So how are we going to do this? Let's move it back to sign magnitude. So which means, remember what do we do to convert a sign magnitude to 1's complement? Just keep the sign bit and flip everything behind it. Similarly, we just do the opposite. That is, we copy this bit, and for the rest, we just flip it. That is 10111. This is sign magnitude. That's negative 23.
Again.
Great, and again.
Real quick, the one that was sign factor, was that not -9? Like, back 2 more. Wasn't this one -9? Negative.
There's a 1.
So
What do you mean?
2 to the 4 plus 2
Yeah,
to the
1, 0.
2 plus 2 to the 1 plus 2 to the 0. This is going to be 4 plus 2 plus 1. That's going to be 7. This is 16. So
Oh, it's sign magnitude. Sorry, I just assumed it was.
it's sign magnitude. Yeah.
So,
But we have 2's complement if it look like this. So for 2's complement, what can we do over here?
We can
Nobody
subtract
assigned.
1.
Subtract 1, right? So we got firstly make it 101000, then make it 1. Keep the first digit always. Then 10111 is going to be minus 23 again. Okay, but
Hopefully it's this easy.
so make sure you are comfortable with this kind of going back and forth stuff. That's just example of how it works. How you might see it in let's say homeworks or quizzes. You might be given, let's say, 1's complement, ask for what's the 2's complement. Oh, by the way, think about this question. If I got the, let's say, A can be any number. I know it's 2 complement. How I know the complement, 2's complement of minus A? Any thoughts?
like how to get it.
Yeah, how to get it?
Flip all the bits and add one.
How do you know that?
Oh, like how do I know?
Yeah. That's right.
Well, it's the same thing as 2 to the n.
Great.
Minus x.
Let's nice. Let's take a look at it. So what your friend is saying, what you do is firstly, but I don't recommend remembering this, but you need to understand this. So firstly, flip all bits. Then add 1. That will do it. The reason behind it, let's say these are all 2's complement. 2's complement. So remember the thing we're going with, let's say, what's the definition of 2's complement? Is 2 to the n minus x if for x greater than 0. So these 2 numbers can be represented this way or maybe the opposite, right? We can put, depends on whether A is positive or negative. Let's take an example, okay? So what if A is positive? Then I will have, let's write this say, sign magnitude as A. So A being a positive number, so it's one's complement, two's complement is always going to be A. And what about minus A? So over here, I need to convert it to, you can start from any places, right? It doesn't matter. So let's say I start from two's complement. I want to convert it to firstly sign magnitude. What I do is swap the first bit of A. Okay, how can we make a sign magnitude to one's complement? We keep the first bit and flip the rest. So which means we are just flip so we flip all the rest of bits. And the third step, we go from one's complement to the two's complement. We do an add one. So if you combine these two operations, what you're going to get is just the flip all the bits. That's right. Okay. So similarly, if you go back, you go from here. Let's see. Why don't we just take a look at example? I think it's the same. It's going to be the same. So let's pick an example. Can someone give me a number from 1 to 7? Sorry? Okay, let's do -5. So 2's complement of -5 is going to be 1011. So what's the complement of 5? 2's complement of +5. So we just flip all the bits, make it 0, 1, 0, 0, and add 1, 0, 1, 0, 1. That's going to be here. Similarly, let's try 3. So you got 1, 1, 0, 1. Flip all the bits, 0, 0, 1, 0, and add 1. You got 0, 0, 1, 1. That's exactly just. Because flip all the bits basically is what? It just means 2 to the n minus 1 minus something. This is our equivalent to flip all bits in X. Right? 2 to the n is just minus 1 is going to give you 1, 1, 1, 1, 1, and you do a minus X. So you are just flipping. If for X, for the corresponding bits, if you have a 1, you got a 0. If you have a 0, you got a 1 as a result. So you're basically flipping all the bits in A. But generally speaking, that's a convenient way I found it. The reason I mentioned is following. We have a question over here. I think I'm missing a question. Oh, here. Let's look at this example. So I'm trying to do a subtraction instead of addition. So in the computer, actually, we don't prefer to implement subtractors. We spend so much time talking about half adders, full adders, and what else? Make it even higher base adders, just like the previous question we did. So I prefer to do addition using complements. That means for any of these, let's say we have this always hold true, which is I will use these brackets to represent 2's complement, but that's only my personal thing. If you use it, make sure you declare it first. Maybe someone can go to Monday's office hours, say what's official, did he mention anything like that?
I don't think so.
And
It usually just says what it.
Okay. I will temporarily use this for convenience. Okay. So if I have some number A and I have another number B, I want to add the 2 complements of these 2. This is equivalent to A plus B. So which means if I want to get A plus B's complement, I just need to make everything 2's complement and add them together. But here we are doing addition. We are doing subtraction instead. So let's take a look. What we are having is the following, which is A, or they are the problem states that these two numbers are already in twos. I think this is trying to represent two's complement, but I prefer using brackets. Okay. So we have a minus b equals to. Now in this case, what I can do is make it following. So a is as it is, but we use a plus and I put the minus b over here. That's why I'm spending time talking about if you have, let's say, minus sevens complement or sevens two's complement, how to get minus sevens. Because in this case, I need to know minus b's complement. And in this case, the first one is going to be 0, 1, 0, 1. What about the second one? 0, 1, 1, 0. Flip it. 1, 0, 0, 1. And plus 1, 1, 0, 1, 0. So I got 1, 0, 1, 0, which is 1, 1, 1, 1 into its complement. By the way, 1, 1, 1, 1 should raise alarm. What is this number? Sorry? Say again? Yeah, minus 1 or negative 1. So you can, and for this kind of questions, because we are only asking typically 6, 7, 8 bits, just to go back to what's this number? It's going to be 5, right? And what about these? It's going to be 6. 5 minus 6 is minus 1. That's the simplest way to verify. If you are more comfortable with, of course, you are more comfortable with decimal subtraction additions. Okay, so move to this bit. That's why I always think something's missing there. There's one more question I didn't do. So here, some more exercise. Join me together in doing this to gain some also familiarity with this. So these are two's complement converted to decimal. How about this? You guys do the first one. You guys do the second one in the middle, and you guys do the third one. I will do it, and you can check your answers with mine. Okay, let's try to practice it. So first 1, 2. Am I doing things correctly?
Yeah, that's good. Yeah.
Okay, great. So I think we're on the same page of these. Do you want to do it again?
Do we have to always go like to sign magnitude?
Oh no, find any way you're comfortable with. But I think it's not a big problem because you are allowed to use computer on site, right? So
And also, are sign magnitude and one's complement like ever used in practice?
not really. Size magnitude may be used for represents for human. Because you see, that's how I found it more comfortable to do this
Yeah.
because I'm comfortable with convert binary to decimal. But for what's complement, because in computer we always use two's complement.
Right.
Okay, but if we all agree we can skip this, right?
Yeah.
I will release the answer after the class, so you just check yours with it. Just practice. Again, this is important because, like I said, the quiz is stressed in terms of time is constrained. So make sure you got some familiarity with these kind of things. So give you any of these, you should be able to finish a row. That's the goal. You need to practice like this, make you sufficient from. Okay, here's something I want to talk about, subtraction. So let's do some normal things. Firstly, let's do subtraction of these two. Remember the trick I just talked about? Move the minus into the parentheses and make it a plus. So then we can apply the rules of a plus b, 2's complement equals a's complement to 2, b's 2 or 2's complement. Okay, so let's give it a try. The first one, 0, 0, this one equals to, the first one, I just copy it. Second one, I'm going to put, let's make it plus and minus 1, 1, 0, 0, 1 into its complement. But this is not a standard form. We have to convert it. 0, 0, 1, 0, 0 plus 1. Flip everything. 0, 0, 1, 1, 0 and plus 1 into its complement. This is going to give me 0, 1, 0, 1, 1. Can you verify?
Yes.
Just check your math. And similarly for this case, I can do similar things by, actually it's going to be the same. It's going to be 1, 1, 0, 0, 1 plus minus 0, 0, 1, 0, 0 equals 2. And what's it? Flip and add 1, 1, 0, 1, 1, and now add 1, make it 1, 0, 0 in 2's complement. So
Forgot to add the one.
Hmm?
Forgot to add the one
sorry.
when you change it to the
Uh,
1, 1.
1, 1,
0,
0,
1.
1, 1. And
But
plus
then you
Oh, then you add the one.
add 1. So it's going to be.
Yeah.
So this is what I'm getting. Because this is going to be thrown away. We only have 5 bits. Let's verify by looking at it. What's this number actually? 1, 1, 0, 0, 1. That's 2's complement. 1, 1, 0, 0, 0. 1's complement. 1, 0, 1, 1, 1. That's going to be a minus 7. And this is going to be 4. What is minus 7 minus 4? That's going to be minus 11. So let's try to convert minus 11 into 2's complement. So firstly, actually, what is the 2's complement for 11? 0, 1, 0, 1, 1. That's going to be 11. Flip it. 1, 0, 1, 0, 1. This is for 2's complement. Okay, I'm doing things correctly. Let's just a quick verify. I do it in different ways. I use this, or I convert it to decimal, but I don't recommend to convert it to decimal during exams. That's not what we're aiming for. But
you can also like take the negative of the leftmost bit, right, and then add all the other bits as positive.
yeah, just find whatever way comfort you. But this is what the reason I'm putting this question is the following, because I start to make this question by doing this. Let's just look at one of these examples. 0, 1, 0, 0 minus 1, 0, 0, 1. What are we going to get into its complement? It's going to be 0, 1, 0, 0 plus 0, 1, 1, 1, which is giving you 1, 0, 1, 1.
Yeah.
But what's this number? 1, 0, 1, 0, 1, 1, 0, 1. It's going to be a minus 1, 1. 1, 1 is 5. Minus 5. You see what happens here? What do we call it? Overflow. So that's something you need to be cautious of. So if you know your for let's say for signed 4 bits, what's the range? So that's the thing you need to consider. What's the range if you have signed 4 bits? So if it's signed, that means you have only 3 digits for numbers. So it can vary from 00 to 111. For positive numbers, we have from 000 to 111, which is going to be 0 to 7. For minus numbers, we have 0 to 7. Yeah, 0 to 7. For negative numbers, we have -1, -2 until -8. We have 8 complements. Imagine the following. So what's the minimum number we can get? Remember the two's complement. Of course, the minimum number means it must be a super negative number. In this case, it must be 2 to the n minus x, which x is greater or equals to 0. Right. So that is two's complement. Okay, so what's the minimum amount you can take for x? It's going to be 0. And what do you have over here? Is 1 0 0 0. Yeah, and this is -8. So this is a minimum number you can get. Similarly, what about, let's say, int h, signed int h? Whatever you get is, I think it's -128 to +127. Similarly, if it's a int, what's the opt case in let's say 32, right? So it's should be minus is to positive 32,767. Remember, they are just a mirror of each other. Remember, we can convert a to -8 of these two's complements, except for 0, because for two's complement, we solve one problem, which is we don't have a -0 over there, right? So, which means you have a missing 1 over there.
Wait, isn't 2 to the 31 like much larger?
Oh no, this is not into 32. This should be into 16. Yeah, 32 is going to give you a greater number, but that result won't change. So if you look at the range, you are going to always going to have one more number.
That's
To
not
be-
even that. That's to the 8. That's it.
Which one? Which
No,
one?
into it would
Oh,
be
yeah,
negative
never mind.
1.
Yeah, this is 2 to the 8, right?
Yeah.
Or 2 to the
No, that's not.
Mm,
Oh,
no,
yeah,
no,
it is.
it's 2,
Yes, it is.
it's 2 to the 7.
yeah, this is 2 to the 7. We have 8 bits, and the first one is used for digits, for signs. Okay, so we are all on the same page of this thing, right? About the maximum range you can get. And similarly, if you think about the lower one, if you remove the first bit, what you are going to get is actually underflow. So you got something is too negative and it goes back to positive. And these are the things you try to avoid. By the way, just for question, if I have a, let's say 10111, it's a signed 5 bits int. I want to extend to 200 bits. What do I do? And zeros? All the zeros on the left hand side. Then it will become sign. I mean, always sign. Yeah. And in this case, you just add ones all the time. If it's two's complement. Similarly, for how to say a positive number, you just always add zeros. Just remember that way if you want to extend them. We talked about this last night.
And if it's a duplicate, we can shrink it.
Say again?
If it's like if it's 0 0, we can shrink it, but if it's like 0 1, we can't. Right.
If it's 0 1.
Like if we have a duplicate, like if it's repeated. So like for example, the bottom one, if it's 0 0 1 1 1, we could shrink it, like decreasing the bits, we could decrease it to 0 1 1 1.
Yeah.
But if it was 1 0, like the one above, we wouldn't be able to decrease it at all.
What kind of circuit will do that? An inverted arbiter.
Yeah.
So now we are searching from left hand side for the first.
Okay.
But remember, for normal arbiter, we are searching from the right hand side to find the first one. But of course, you can add few not gates to implement this. This kind of mind exercise, do it all the time. Then you will be faster in solving, using this combinational block to build something else. Okay, but never mind. We have this practice. So we are just doing addition of these numbers, 2a plus 3c. So of course you can do it in brute force, which is 2a plus 3c, a plus c, great. A is 10, b is 11, c is 12. So what I got is 22, right? It's hexadecimal, which is base 16. So I got carry over 1, and what is 22 minus 16 is 26. And similarly, 2 plus 3 plus 1 is 56, 66. That solves it. But apparently, someone finds it's not so comfortable. Remember for hexadecimal, because hex is base 16, and it's 2 to the 4, which is the exponent of another base. Then we can just make it base 2, which is, what is 2? 0, 0, 1, 0. I'm using 4 base because 16 is equals to 2 to the 4. And A, 1, 0, 1, 0. 3 is 0, 0, 1, 1. C is, let's add 2 here. So it should be 1, 1, 0, 0. And let's add them up. So what do I have here? Carry 1 and 0, 1, 1, 0. Over here, 0, 1, 1, 0, 6, 6, right? Same case, just define whatever makes you comfortable again. But what if they ask you base 8? You can just use straight base. What I mean is, let's say I have, for example, these are base 8 numbers. So I can, I can split each number into 3 bits, 1, 1, 1, 1, 1, 0, something like that, and do this one. You can see the same idea applies to one trick. We try to, for example, build a larger decoder using smaller decoders. So we decouple let's say we have input 6 bits. We are using 2 to 4 encoders. So we split into 3 2, 4 encoders as an input. Then we look at what are the first 2 bits represent, which line will be on, which line will be on, which line will be on, and we use AND gate to connect these 3 cases to make the unified one. That's how we build it. It's the same idea, just split and recombine. So, okay, this question is interesting. Well, how much time do I have?
20,
Great.
17.
I really want to finish 5 and 6 because these are pretty important questions.
Okay.
So we have, this is what a circuit I want to build. On the, wait, let me refrain the temptation to directly put my hands over there. Otherwise, you won't see anything on the recording. So on this side, we have something called the BCD code. BCD code means we are trying to represent a decimal into binary, which is just the normal thing we are saying, except for we don't have anything greater than 10 is going to be illegal code, which is going to be, in our case, let's just make it don't cares, okay? And for excessive 3 code, C code, what does this mean? You can see it's 0011, 0100. So yeah, that's why I call excess 3 code. You just make a +3. So BCD +3 is going to give you excess 3 code. We are using this because I can just give you intuition, but I won't go deeper into that. Sometimes I want to implement, let's say, circuits for decimal adder. For example, a 1-bit decimal, a few bits of decimal adders, like what we normally do, 9 plus 1 equals to 10, right? And in this case, excessive 3 code is going to make it easier for you to judge whether it's going to be a carry or not. If you're, because you have to represent things in terms of zeros and ones, but compared to using BCD code directly, excess 3 code helps you to generate the carry faster. That would be one of the benefits, but I won't go deeper into that. Just imagine there's one boring person in this world implement this excess 3 code, and someone who is even more boring, which is me, ask you to do the following: build a circuit to bidirectionally encode, decode these 2 codes, which means I have a control signal K. If K equals to 0, then I'll ask you to convert BCD code into excess 3 C code, right? From left to right. And if k equals to 1, it's right to left. Some of your friends already captured that, which is if you go left and right, what do you do? +3, right? And what if you go back? -3. But remember, BCD and XS3 code are both unsigned. That's going to be a little bit tricky over here, but let's try to tackle it. For the time constraint, I won't give you time to even make attempts to think about it. I'll directly jump into conclusions, but make sure you think about why is it the case. So, but the intuition is just what I said. For k equals to 0, the cases we do +1, other case +3, other cases we do -3. So what are these? We're going to do +3, right? It's going to be use a 4-bit adder. Okay, let's start with that. I have an adder. Let's say we have an adder with let's call it P and let's call it Q. So we are doing 4 bits P plus Q, 3 to 0, 3 to 0. But if you remember one thing, which is going to cause complications, these are all unsigned numbers. So what do you think we can do? How about we just use another 1-bit adder over here? A, B, S, and C out, C in. Of course, we also have a C in. You see, one good thing about adder is, however complicated it is, they always have only one C in and one C out. And the summation is going to be also 3 to 0 or 4 bits. And there's no doubt if I connect what do you call it? BCD. Let's call it what is it? From A3 to A0. Okay. This is of course what we need to do. Then so if you agree with me, A is always going to be 0, right? So now we have one style. Let's maybe connect the C out to C in. So you see, this is a 5 bits signed number of our BCD code, or whatever excessive 3 code, our source code. So this is 5-bit source. Okay, what about Q? What should we put here? So Q equals to, let's put the BQ. So Q is 4 bits, B is 1 bit. Okay, so we put it as a single number. So what is +3? +3 is 0, 0, 0, 1, 1. If k equals to 0. So we +3 if k equals to 0. In other cases, what is -3? We need to minus -3 from the code, original source code, which is 1, 0, sorry, 1, 1, 1, 0, 1. Does it make sense? Okay. Let's move it down. So firstly, we can put a B over here. Let's just put a 0 or 1. But can you confirm? Not really. Let's just continue with what we have. So for the lowest bit, if k equals to 0, this is just a short k map. If you don't feel like it, draw a real k map. But k equals to 0, k equals to 1 is always going to 1, which means you can just put a 1 over here. Similarly, this bit, wait, do we have any other bits? No. Okay, so these 2 bits are, I think they are k, right?
Oh, sorry.
This is inverse k, yes. So this is not k. So let's put k and put a NOT gate over here. So this will go here for this digit. And the original K will go to the first two digits. And of course, K also goes to B, right? And this is going to be S. So our output is going to be, this is a digit, and this is going to be S0. So this is going to be our final output, which solves the problem. But we can do some simplification by looking at this question, which is for these numbers, if you do +3, you will always get a positive number, right? And for this number, because we are limiting the maximum number to be 9. So for this code, if you -3, of course, you won't get anything below 0. So which means whatever you do, that's because the root cause is because the limitation, your input is limited. In this case, whatever your K is, actually, this bit is always going to be 0 because you always get a positive number. That's based on our observation from this truth table, right? Whatever you do +3 from here to here or do -3 from the other direction, you won't never get a negative number. So which means since it's always 0, then no need to use all of these. Let's just remove it. Oh, wait, I go too far. Not really. So this is our input. But I'm showing that because this doesn't come for granted. This is only because we have a very limited input and it happens to be this case. In other cases, if you are trying to do -3 on a positive number, you always have to, of course, add additional bit for symbol, make it 5 bits. Then you start to do this kind of things. Okay. But which means be flexible. Don't have a stereotype that if I'm doing +3, I'm going just to make 2 numbers. What if I'm not doing BCD code, but I have a few more rows down below? Then you might sometimes get negative numbers like overflow or something. You need to tackle that thing. So that's why we ask you to do those test vectors in logic for corner cases. But in this case, because we already list every possibility for you, and you can just verify this adder will do it. So you can see what we are doing. This adder is just the conversion between these two numbers, such as the plus and -3. So yeah, go ahead.
Yeah. Does this? I was looking at this. If you plug in XS3 for 0, it doesn't look like you get BCD for 0. We get 1. We would get whatever.
Let's give it a try. So what is BCD for? Wait, where is it? This one?
XS3, yeah.
Okay.
And convert it to
0, 0, 1, 1.
BCD.
And this is a number again.
It'll be 1.
So
you have 1, 1.
Yeah, K would.
You have 1, 1, 0, 1 plus 0, 0, 1, 1.
it will be 1 and got a 1, 0. Is that right?
Wait, I got 9 on it. No, 1, 1, 0, 0.
Yeah, 1, 1.
Oh, I got 1, 0. No, which means it's something is not right over here. Let me check. So we are trying to do -3 in this case, right?
Mm-hmm.
So -3 means I'm just the plus 3 is complement. Sorry?
We just did on the
Should.
brain,
1.
because you carry the 1
Yeah.
from the second.
Oh, I carried a 1 over here.
Uh,
1 plus 1
Zero,
is 0.
zero.
I carried a 1 over.
okay.
Oh, okay.
Okay.
No problem in that case.
Wait, never mind.
Okay, but nice try. So now we are all good with this. Any other questions? Okay, for question 6, I think I still got a couple of minutes. Let me quickly finish this. So again, this is what I'm saying. Building using adder, I'm saying using two 4-bit adders and necessary logical gates. Or you can prefer, if you prefer, you can use components to implement a 1-bit decimal adder, which is you have two inputs, two 4-bit input, A and B, and you are outputting S and CO. But S over here will be, the range will be from 0 to 9. And if the A plus B is greater or equals to 10, then I will get a carryover, which is just what we normally do in a decimal adder. And you get what I'm trying to say. This is going to be similar as before, as a previous question. So let's give it a try. So of course, the first thing, we are asking you to add two numbers, right? So first thing, of course, we use the adder to combine A and B. The 4-bit adder to combine A and B. That's the most trivial thing we have. Of course, C will be grounded. I will not draw C in this case. This is A, this is B. We got 3 to 0, 3 to 0. And output will be, let's call it S0 and C0. Okay, and the next one, what we are trying to do is the following. I can put another error. This is for processing the. So remember, this is some S0 is a summation we are going to get, but we are building a decimal adder. So which means if S0 is greater or equals to, I would say equals to 10, then we need to do a -10 on these. Let me, for simplicity, I will just make it a plus. So, thank you. Yes. So in the second adder we are trying to do is, of course, -10, right? So this is what we are doing. But actually, it's an if-else case. So if S0 is not greater or equals to 10, then what we do is +0. But in other cases, we'll do -10. So you can see this kind of have the similar taste with the previous question. So for the first one, for number A, 4-bit, I will just copy it SO. But for B, it's going to be two cases. So if CO equals to, obviously, just to be aware of one thing, which is 1111, 1111. This is worst case. It can give us 5 bits, right? And in some cases, it's not even like this, but even smaller number. So you can, if you look at SO itself, it's actually less than 10. But we still need to carry over because this number is going to be 30, right? 15 plus 15. So in this case, so what's the condition of we need to do a -10? Either we have a CO or
you're not, I think you're adding on there. Would it be 1111?
okay, let me use another example.
There,
Yeah.
okay.
This is a better corner case.
Let's,
Okay, this is only 7, but still we need to do carryover, but because the final number is pretty large. So which means if we have a carryover, of course, we need to do a -10. What else? What other cases? That is SO greater or equals to 10. These only two cases we need to. And in this case, S equals to A minus 10. So this is S, and we got, for this circuit, I don't expect to use a CO, but we have, remember, it's we have a final output as a C out. So for this one, it's going to be triggered by this signal, right? So if this case, which means S equal to A minus 10 and C out equals to 1. In other cases, S equals to A and C out equals to 0. Okay, so again, just like before, what is input of B? Let's say we have a signal for this if, okay. So which means this condition is connected to this bus. And so -10, what is -10? Let's make it 5 bits. So it's okay. So firstly, 10's choose complement is this. And we invert it and +1. Yeah. This is the 2's complement of -10. So just like before, I can remove the top bit because I'm just add 2 positive numbers. There's no reason you get something negative, right? So, but you can double check. You can just import it temporarily and you found it's always going to be 0, so I can discard that part. But I will just directly skip it for the same reason as before. Then so I need to do 1 0 0 1 in the top case. So which means B equals to 1 0 0 1 1 0. In this case, B equals to 0 0 0 0. So for this signal, you can see for 3 bits I get the first one and the last one will always going to be grounded, and this signal will go to here and here, and also it will also serve as C out. Okay, so the final step is let me copy it over here so we have more space. Okay. And by the way, let's call it C and D to avoid confusion. C and D. So in this case, S equals to C minus 10. In this case, we will equals to C. And the top case indicates we got D equals to 0 1 1 0 based on the reasoning over here. Otherwise, D equals to 0 0 0 0. Okay, so then how do we generate the signal of CO or S0 greater than 10? Of course, there's one module we can directly use. What is that? Magnitude comparator. But remember, we need to put, for example, we can do the following. Let's say this is a magnitude comparator, and this is a GT signal. I can put 10 over here. I put SO over here, and put a NOT gate over here. It makes sense, right? So this is going to be 1 if SO is greater than 1.
You want to put 9 instead of 10, so that it's greater than or equal.
Okay, that will work too. I'm putting, but that would be more, yeah, that would be more simple, which is I can put SO 9, and then we don't need an inverter. So this will be OR with CO. I can put a huge OR gate over here. Can you confirm we still have 6 minutes? Because it's I think you guys agree with this solution, right? If we are using a combination of blocks, we can, because this is a function we are trying to achieve, then either CO or SO greater than 10. So we just take SO and put it in a magnetic comparator with 9 and greater, or we have CO. That's just the write down what we are writing in English or in programming language. But if we move back, we asked for logical gates. So which means actually you will find it's not necessary to do such things. Let's come back. So CO won't change, but let's think about SO greater than 10. SO is a 4-digit number. So we are just implementing I asked you to implement a minimized circuit for this. So what would you do? Your output will be 1 bit GT.
You want to just check if like the 3-bit and the 1-bit are both 1.
Yeah, that will work. So which means you just list all the cases where SO greater than 0 and try to end it. But for a more systematic approach, how about we do the following? We just have a truth table, which is GT will be 0 for this starting from 0, 0, 0, 0 to 1, 0, 0, 1, which is 9. Okay. And for 10 to 15, which is 1, 0, 1, 0 to 1, 1, 1, 1. The output will be 1. So we can get a 16-row truth table of this. Okay, then you guys know what I'm going to do. But watch me for any possible mistake. This is came out a very error prone. See, errors. Okay, so we have from 10 to 15, this is going to be 1. So 0, 1, 2, 3, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 12, 13, 14, 15. That's it. Does that make sense? So because the final GT is equal to summation of mean term 10, 11, 12, 13, 14, 15. So I'm converting it to a K-map. Then circled using prime implicants. So this is very simple. From what I circle, you know the final expression won't be very complicated because it's a large circle, cover a lot of space. The more you can cover, then the more simplified your final answer will be. Let's look at this one. So just circling what. So let's call it S03, S02, S01, S00. I don't recommend you remember everything because remember money will give you some tricks like he will swap these things randomly. Just make sure what you are you just copy these into the K-map. Make sure each of these elements have a correspondence with a row in the truth table that we do it. I'm doing this because it's my personal stuff, so I can order everything in DCVA and I can just order the truth table from 0 to 15 in incremental order. Then I can do what I'm just doing, which is I believe faster. Okay, so the final thing will be S03 and S02, or what's this? S03 over 1110, so S01, S03 and S01. You shouldn't have any problem with these. Otherwise, make sure to talk to me during office hours. You are way behind in that case. I made a mistake.
No, you like take that and factor out in S03.
Sure, why not?
You need a not S02 on the right.
What they are saying is what you can do is SO2 or this will save you 1 gate probably, but this is also acceptable because how to say it's a minimized SOP form. No, it's SOP. It's sum of product.
The bottom one.
Okay, yeah. But it seems like, you know why? If you do the other direction and you do max terms and you circle the zeros, you will have even larger circle. This is the first one. This is the second one. So the smaller circle, which has 4 elements, correspond to these, and the larger circle covers 80 elements is this, right? Okay. Does it make sense, actually? Oh, no, that's max term, so I have to invert it. No problem. Okay, so finally, let's go back with, let's take this one. So let's do a final step of our circuit, and I can remove this. One last thing. Okay, this is one. So let's. Oh, I will use the splitter if it's okay for you. This is the final step. 3 bits to 0 bits, and of course, I will observe it and put it here. But now I will have X03, which is this one. Let's drag it over here. And SO2, SO1. So we use OR gate to connect these two, and an AND gate to connect these two, and put the OR gate over here to incorporate the CO signal, and put it here. Sorry, let's drag it. I will do it, but I will clean it up when I post this annotation. But this is just to implement the circuit using a few gates, which is trivial. Okay, so much for today. And if you can, make sure attend this tonight's session.
Thank you.